Allergies occur in susceptible individuals when the body's response to a protein or allergen for a foreign pathogen may be harmful rather than protective. When first exposed to the allergen, the immune system is activated to respond to it. Allergic sensitization begins when the antigen is taken up and processed by regional antigen-presenting cells, or APCs, and presented on a Class II major histocompatibility complex, or MHC, to T helper Th cells. For reasons that are still not entirely clear, in susceptible individuals, a shift towards more of the Th2 cell subtype is established. Other types of Th cells may also play a role. The development of memory cells then takes place. This involves the differentiation of allergen-specific CD4 plus Th2 cells, which produce the cytokines IL-4, IL-5, IL-9, IL-10, and IL-13, among others. These cytokines then signal towards B cells and directly interact with them. B cells switch their production of antibodies to the IgE isotype, which may be released locally and into the bloodstream, where they can bind to receptors on the surface of mast cells, basophils, and APCs. Upon re-exposure, receptor-bound IgE molecules are cross-linked by the allergen, resulting in the release of mediators from the mast cells that lead to hypersensitivity reactions. These mediators then bind to their receptors in various tissues, leading to allergic symptoms. Sometimes these reactions are severe systemic allergic reactions that can be life-threatening, such as anaphylaxis, which may require emergency room visits and may lead to death if not treated promptly. Currently approved allergen-specific immunotherapy for environmental, respiratory, and food allergy may involve the subcutaneous or sublingual administration of doses of the allergen with the aim of desensitizing the individual. Though not yet approved, other routes for immunotherapy for food allergy possess the potential for the development of alternative treatment options. During the initiation phase of treatment, repeated low-dose exposures to an allergen can suppress effector cell responses as mast cells and basophils become desensitized over time. Allergen-specific immunotherapy may suppress allergic responses both directly and indirectly. This may occur in part due to reduction of the Th2 cells. Anti-inflammatory cytokines such as IL-10 and TGF-beta are also produced by Treg cells. IL-10 leads to downregulation of MHC2 molecules on APCs and downregulation of eosinophil activity, while also inhibiting a wide range of pro-inflammatory cytokines, such as IL-5 production by Th2 cells. This reduces tissue inflammation and mucus production. Meanwhile, TGF-beta inhibits B-cell proliferation and differentiation, while also decreasing allergen-specific IgE production. With a decrease in allergen-specific IgE, B cells are induced to produce non-inflammatory IgG4. IgG4 levels are slightly increased, typically within the first 12 months of starting immunotherapy, becoming significantly higher by year 2. And has been linked to suppression of effector cells by 2 mechanisms. IgG4 is thought to capture the allergen before it reaches effector cell-bound IgE, thus preventing activation of local mast cells and basophils. IgG4 also binds an inhibitory receptor on basophils, thus preventing their degranulation. By continuously stimulating the immune system, for example, by gradually escalating the allergen dose, the individual may reach a less reactive, desensitized state to protect against reactions due to accidental exposure to the allergen. However, sustained desensitization leading to tolerance has not been proven and may require prolonged exposure to the allergen. Further understanding of how effector cells are desensitized at the molecular level may lead to new therapies for allergies.